All right, so let's try a couple more. The fan blades on a jet engine have a moment of inertia of 30. Well, that was convenient. We got that already. Okay, in 10 seconds, they rotate counterclockwise from rest. Okay, so counterclockwise would be that way. Okay, so let's just call that positive. Up to a rotation rate of 20 revolutions per second. Okay, so I'm going to start to make a little list over here. 30 time 10 seconds. Okay, a rotation rate, right? That's an omega, right? That's that angular velocity. 20 revs per second, which we're going to need to turn into radians. Okay, what torque must be applied to achieve this amount of angular acceleration? Okay, so it looks like we're going to need the angular acceleration also. Okay, so the first thing is we can see this would be like the omega final, okay, which would mean the omega naught would be 0. Nope, not meters, sorry. Radians. Okay, radians per second. Okay, so 20 revs per second. Remember, one revolution or once around the circle is going to be 2 pi radians. Okay, so that's going to be 40 pi radians per second. Okay, so the angular acceleration is just the change in velocity, angular velocity over time. So it's going to get up to 40 pi radians per second in 10 seconds, which is going to be 4 pi radians per second. And I can just get that as a number. Oh, heck, I might as well just get it as a number. What the heck? 4 times 3.14. 12.5. 12.6. Let's just round it, huh? Okay, 12.6. Okay. Oh, radians per second squared. All right, because it's radians per second. Okay. All right, and now if I need to know the torque, okay, I'll do the sum of the torques equals I alpha, all right? And then we'll assume that there's only going to be one, right? Because it doesn't say anything about friction. So, and they just asked for torque, so I don't have to split that. So basically, I'm just multiplying these together. Oh, that was easy. Okay, they gave the I already. How convenient. Okay, so the torque is going to be 30 times 12.6. So you really just want to think linearly, right? 378. Remember, torque is in Newton times meter. Okay. Yeah. You really just want to try to think of it as if it were linear. I think that's easier. Okay. All right. And then the next question is, what is the tangential speed of a bug that is sitting at the end of the rotor if it's 2 meters long? Okay, so a bug that would be sitting right out there, okay, if this angular acceleration at that, the angular velocity at that point is 40 pi radians per second, okay, remember the tangential speed is just times the radius. You always multiply by the radius to go to linear from angular, right? Because you're trying to get the units right. Okay, so if it's a 2 meter blade and it's a 40 pi radians per second, right? Remember, radians doesn't count. Oops. Okay, that's how you're going to get meters per second. Okay, so 80 pi, or if you want to be really happy about having an actual number, sure, running out of space, but fine. 251.2 meters per second at that point. Okay, so that's how you get to that. Okay, all right, I'm going to do this one on the same video just so I only have to put one. Okay, uniform cylindrical grinding wheel has a mass of 50 kilograms and a diameter of 1 meter. Ooh, tricky. So radius 0.5 is turned on by an electric motor. Okay, the friction in the bearings is negligible. That means like in the part where it's turning. A tool whose coefficient of kinetic friction with the wheel is 0.6 is pressed perpendicularly against the wheel with a force of 40. Okay, so look, if you want to think of it like this, right? Think of it like this. I'm pressing down with this force, okay, right? And so that's going to make a, how can I draw this? That's going to make a friction force right here, okay? So that's just like a normal force. Okay, friction would be mu times that force, right? Because that's how hard they press together, and times the mu, okay? So the mu is 0.6, and it's getting pushed with 40, so that's going to be 24 newtons is going to be the friction here, okay? right? So then that friction, since I'm pushing inward, right, that's the radial direction, so that's not going to change the speed, but the fact that they have this friction force here, like say the wheel's spinning this way, the friction would act opposite. Okay, that's going to make it slow down or, well, slow down in this case, or it could be speed up if it was the other way. Okay, right? But this force 40 doesn't count because it's in the radial direction, so that's not going to change the speed. Okay, all right, now they're asking what torque must be supplied by the motor to keep it at a constant angular velocity. Okay, so basically we're trying to say, so this would be like if we have a box or something pushing it across the floor, it has some friction, you have to apply some other force to keep those balanced. Okay, so that's what you're doing now, except with the torque. All right, okay, so the sum of the torques is going to equal 0. Right, so let's say the torque from the motor is going to have to equal the torque from the friction, right? Okay, because that friction force is trying to slow it down, so the motor's going to have to crank some kind of a force to keep pushing it, to keep it from slowing down. Okay, and they're just asking for the torque of the motor. All right, so basically that's just going to be the friction force times the radius. Okay, the friction force we already figured out is 24. Okay, times the radius is 0.5, which is 12 Newton meters, would be how much torque that the motor has to supply. Okay, to keep it moving at a constant angular velocity and not slow down. Okay, that wasn't so bad. Check.